Hi there, welcome to the third part of Lesson 7. This is the applied part of the lesson, in which we play with RStudio. In this lesson, we will consider the same topics we have already discussed in the theoretical lessons we just had from an applied point of view, using R and making our hands dirty with data. We will start from the simple seasonality example that we considered. You remember the one with the cosine-shaped seasonal trend. After that, we will say something about the estimation of ARMA and ARIMA models, and I will try to teach you how you can quickly get some heuristic from the analysis of your time series. Okay, so we start by creating a time series with a seasonal component as the one that we considered in the first part of this lesson. Okay, this time series is written down as you can see on your screen, and it has a cosine seasonal component and a white noise around this. This is a realization of this time series. Since I set the seed, you should be able to get exactly the same result. If we plot the ACF of this time series with ACF of x, what we get is a typical ACF indicating the presence of seasonality in the data. In fact, you can see that we have a certain number of significant lags, then the lags become not significant, but again, they change the sign and become significant after a certain delay. This is a typical pattern of seasonality. Using some well-known trigonometric identities, we can introduce the quantity z1 and z2 that we can then use in our linear regression to take care of the seasonality in the data. Now, notice that since we want to fit a regression without the intercept, we add -1 in the LM function. What we get is exactly our fitting of the seasonal trend. Let us plot our time series with the superimposition of the trend we have just estimated that you can clearly see as the bold line on the plot. Now, if we consider the estimates that we got from our regression, we see that for what concerns the residuals, we can observe some symmetry which is compatible with normally distributed residuals. Remember that we are performing OLS, so we want the residuals to be normally distributed. And for what concerns the estimate, Z1 and Z2, they are both significant if we look at the t-value or the p-value, or simply we take the estimate and we divide by the standard error. The usual diagnostic of the residuals that we can get by typing plot fit tells us that actually the residuals of our regression for the seasonal trend are somehow normally distributed. The QQ plot, the scatter plot of the residuals against fitted, the scale location plot, they are all consistent with normally distributed residuals. Since the original time series was made of a seasonal trend plus a white noise, once we remove the trend, we see that actually the residuals are a white noise. So we were able to remove all the dependence. Remember that the first leg in the ACF makes no sense because it's the correlation of an observation with itself. Okay? Now, we can deseasonalize the same time series also using the STL function. But in order to use the STL function, we have to create a time series object. So we can use the TS function. We give a starting date that we choose randomly, and then we have to specify, this is very important, the periodicity of the time series. Let's assume that our observations are weekly observations. Now, once we do that, we can use the STL function, and the STL function will give us the following result. It will give us the seasonal component that is estimated, the trend that is estimated, linear or polynomial, and the remainder. The remainder is what remains after removing the trend and the seasonality. Okay? Now, what is very important is to plot the result of our STL function, and we get a plot that we have already seen in our first part of the lesson. In this plot, we clearly see the original data, the seasonal component, the trend, and the remainder. In this plot, I told you what is very important to observe is the gray bar on the right-hand side of the plot. Why? Because this bar tells us what is the scale of the different components. So, for example, we see that the scale of the trend with respect to the original time series is very small. So, in a sense, as we know, because we created the time series, there is no trend here apart from the seasonal component. And if you remember, this was evident by the fact that in our time series we had our seasonal part and the white noise. There was no other particular trend. If you use the STL function, it's very simple to verify that obviously the sum of trend plus season plus remainder corresponds to the original time series. Okay, so here we just show that for the first observation, but it is clear that the three components sum back to the original data. Now, if we consider the ACF of the remainder of the STL function, we see that also here we are able to remove all the dependence in the data, which is only the seasonal part. We now see how to fit ARMA and ARIMA models in R. For pedagogical reasons, we start from a time series that we simulate using the ARIMA sim function. So this is an ARIMA 1, 1, 2. So with one leg in the ARMA part, integration 1, and 2 legs in the moving average part. On screen, you can see a realization of the process, of which we can also consider the ACF and the PACF. The ACF suggests the presence of a trend, as also evident from the plot of the time series itself, and for what concerns the PACF finds that there is still some dependence to be studied after the removal of the trend and the seasons and all the other things. But remember that when you see an ACF with such a long memory and you know that you have not detrended the data or removed the season and so on, the PACF is not completely reliable. Okay, so the combination of the ACF and the PACF that we have in this case tells us that for sure there is some dependence in the data, but we cannot clearly identify this dependence until we do not remove the trend, the season, and so on. By using differences, we can try to take care of trends and mild seasonalities. So what we can do is just use the diff function to take our differences, and then we can check what happens to the ACF and the PACF of the new time series. Now, what you see on your screen is the difference time series. For what concerns the ACF, we see that obviously now the memory is shorter but still present, and for what concerns the PACF, it has changed. We have a higher number of significant lags, suggesting that actually once we remove part of the trend, then it is easier to see the real time series behind emerging. Since we have considered first order differences, it means that in an ARIMA world we are setting d equal to 1. As I told you, d is very rarely larger than 2 in modeling, and for sure it is almost never larger than 2 in finance. Now, using the ACF and the PACF, we can try to have an educated guess about P and Q of the ARMA model we will try to fit to the data. Now, the ACF has 6 significant legs, and for what concerns the PACF, we find 4 significant legs. Now, it means that the PACF has a shorter tail with respect to the ACF. In this situation, what you typically find out is that the sum of P and Q will be always smaller than the number of significant legs in the PACF. So we can expect P plus Q to be smaller than 4. And since the ACF has a slightly longer tail, we will tend to say that the moving average component has an order which is larger than the autoregressive part. The heuristic for ARMA model is the following. Now you look at the ACF and the PACF. The sum of P plus Q will always be smaller than the shorter of the two plots. So if in the ACF or the PACF you find that the smallest number of significant legs is 3, then P plus Q will be smaller than 3. If that number is 6, maybe in the ACF or the PACF, then the P plus Q sum will be smaller than 6. Now, in order to then understand possibly the value of P or Q, we can look at the tails. If the ACF prevails, so if the ACF has a longer tail, then we tend to say that the moving average part will have a higher order. If conversely it is the PACF, we will say that the autoregressive part will have a higher order. But in general, for ARMA models, what I tend to suggest is just to use the rule to find the sum of P plus Q. Then the choice of P and Q, I think that it is better to play with other tools like, for example, the Akaike information criterion and so on. Let's now consider the problem of estimation. We will use the ARIMA function for that, which is a quite powerful tool in R. Now, what we will do in the following is to start with the original time series, and out of this time series of 500 observations, we will consider 480 observations. We will use the last 20 observations to check our forecasting. Okay, so we will have an in-sample and out-of-sample use of our observations. Now, for what concerns the analysis of the data, we will start from the original time series, so the one without the differences. In that sense, you will see that we will fit an ARIMA model in which the D parameter is 1. If, conversely, you want to start from the differenced time series, the one that we have already created using the diff function, then you should fit an ARIMA model with D equal to 0. Okay, you will see that you get essentially the same results, and I leave this check to you. So you can just reperform all the things that we will do together, but change the parameter D from 1 to 0. Given that we expect P plus Q to be smaller than 4, we will fit a certain number of ARIMA models in which the P and Q parameters give combinations smaller than 4. So we consider, for example, an ARIMA 012, an ARIMA 110, an ARIMA 112, and so on, as you can see on your screen. We can then compare the results of the different fitting exercises. What we do is to check that the estimates we get are significant, and we will also check the Akaike information criterion. That for the moment is the criterion we are using to perform model selection. Among the 5 models we have fitted, the model with the smallest Akaike information criterion and all parameters significant is the ARIMA 112, that is to say, model 3 in our list. A simple trick that I suggest to use is to build a loop and to use this loop to verify all the possible combinations of P and Q. Okay, an example is on your screen. It's very simple. You can for sure do better. What we do is just to fit different ARIMA models with different combinations of P and Q. Remember that D is fixed to 1 for us because we know that we just consider the first order differences, and then we store the Akaike information criterion for each different model. These Akaike information criteria are in the table you see on your screen. As you can observe, the minimum is reached in cell 2, 3, that actually correspond exactly to the model we have seen before. That will be, considering the way in which we have defined the indexes in the table, corresponds to one leg in the autoregressive part and two legs in the moving average part. Please notice that the Akaika information criterion is one of the things you have to check. In fact, if you consider, for example, the ARIMA 212, you find that its Akaika is one of the smallest in the table. Yet, this model makes no sense because the estimate of the second autoregressive component is not significant, okay? So you should never pick a model just on the basis of the Akaike, but you have to check if the model makes sense, if all the parameters are significant, and so on. So don't be fooled by just picking one criterion and sticking to that criterion without any critical attitude. This is extremely dangerous, okay? So the Akaike is okay, but then always check if the model makes sense, if all the estimates are significant, and so on. Moreover, in using the Akaike information criterion, remember that there is a trade-off between the value of the criterion and the number of parameters. Remember that we want a parsimonious model, so always choose wisely your model, because it makes no sense to look for the mere minimization of the Akaike if in order to get that you have to use a lot of parameters and every step is just a ridiculous amount of decimals in the decrease of the value of the criterion. So if we go back to model 3, we can see that this model is actually consistent with the data we have created, is an ARIMA 112, and the parameters we get in our estimations are also consistent with the parameters we have used for the simulation, okay? Just consider that we are using a relatively small data set. So if you increase the size of the data set, you can for sure improve your estimates further. Once we have estimated our model, we can try to perform some prediction. One way to do that is to use the predict function, which is a basis function in R. With this function, we can tell R how many observations we want to predict, say the next 20 observations, so we can also compare those observations with the observations we kept aside from the original dataset. And since the predict function also provides standard errors, we can use that information together with the standard quantiles of a normal distribution to build confidence intervals. Here we choose a 95% confidence interval for our estimates. Now, as you can see on your screen, the dashed red line represents the expected behavior of our time series in the future, which is somehow consistent with what we have observed, the continuous black line. For what concerns the green lines, these are the confidence intervals. Now, the same result can be obtained in a little bit fancier way using the forecast function in the forecast package. What you get is exactly the same result. Now the blue line corresponds to our red dashed lines and the confidence bands are provided automatically, okay? If you are particularly lazy, you can also try to make R fit the ARIMA model directly for you using an automatic function which is auto-ARIMA. If you use the auto-ARIMA function, you just provide the dataset that you want to use as training dataset, and you have to provide the information criterion to be used for model selection. If you do that and you choose the Akaike information criterion, you get exactly the ARIMA 112 model, and the results you get are exactly the results we got before using our step-by-step procedure. So in a sense, we did a decent job so far. If you want, you can also change the information criterion. For example, you can use the BIC, the Bayesian information criterion that you see on your screen, and using that criterion, the auto-ARIMA function identifies the same model. So it's still the ARIMA 112, which makes sense because these are data that we have generated from an ARIMA 112, so it's not such a problematic data set. In general, it's not guaranteed that you get the same results by changing the information criterion. My suggestion is never to trust the auto-ARIMA function too much. It's always better to perform your analysis step by step, and you can always use the auto-ARIMA function as a sort of check of what you have done. If the results you get with your procedure and the auto-ARIMA functions are very different, then you can start thinking if you did something wrong with your data, and you can maybe start again with your analysis, okay? But my suggestion is never rely too much, never over-rely on packages. Okay, that was it for lesson 7. In lesson 8, so in the next lesson, we will complete our analysis of time series, at least what we want to know about time series. We could have many courses on time series, but for us, just what we need to know, we will consider Arch and Garch models very briefly because they are essential to play with volatility, to model volatility. After that, we will finally enter into the real risk management part of the course by introducing the different types of risks that we will model using the tools we have been considering so far.